Hi there, this is Professor Shannon Gracey from Maricosta College. Today we will be covering section 3.4 from the Larson and Edwards Calculus text. So go ahead and get ready because, drumroll please, today we'll be determining intervals on which a function is concave upward or downward. We're going to learn how to find points of inflection of the graph of a function, and then we'll learn about the second derivative test, which also finds relative extrema. So why don't you pause the movie and warm it on up, and we'll see how you did. Okay, let's see how you did. So for this one, we've been given the graph of f prime. And this is going from -10 to 10. Increasing intervals on the original function mean good, positive derivative outputs, positive slopes. So if we simply highlight the parts of our graph that have positive outputs, and then we can basically just look at the intervals about the horizontal axis where that is true. So it looks to me like we cross the x-axis here. So these are going to end up being your critical numbers that you would have found by setting the derivative equal to 0. So you could call these C1, 2, 3, and 4. And then what would you say C1 is about equal to? It's close to -9, right? So we could probably call that -8.7 or something like that. Sound good? So we start out at approximately -8.7 and we go until, good, C2 is at about 1, 2, 3, 4. So maybe -4.2 or something. I'm just estimating, approximating. And then we have one more interval, right? So C3 is at about -1.7. And it goes until C4 where we have positive outputs for our derivative, and that is at about +8.7. Okay, so far? So those are the domain intervals on which the original function is increasing because those are the intervals where the derivative function is positive. Now, if you look at the decreasing intervals, you just go where they've dropped below the x-axis. And it looks to me like we have 3 intervals here. So again, we'll go -infinity to C1, which we said was about -8.7. And then that second one is C2 to C3, which is going to be about -4.2 to -1.7, and then the third interval is at the very end. It starts at C4, non-inclusive, and goes to infinity. Good so far? Okay, so we've already actually done this part. Well, sort of. We've ascertained that there's a 0 derivative at the C1, 2, 3, and 4. So basically, what was that thing about the first derivative test? If you go from a positive derivative to a negative derivative, it's like you're going up the hill, then down the hill. So that would be a relative max. A negative derivative to a positive derivative is like down the hill and then up the hill. So it's a relative min. So at C1, which is approximately, because that'd be going negative to positive, so that'd be a relative min. So C1 we said was approximately -8.7. And then again we go from negative to positive at C3. And C3 we said was approximately -1.7. And then the maxima are when you go from positive to negative on your derivative. So those will be at C2, which was approximately -4.2, and C4, which is approximately 8.7. Okay? How you doing so far? Great, awesome. Okay, you feel all warmed up? Very good. All right, so now we get into concavity, right? So the definition for concavity, again, you have to have your function be differentiable on some open interval. And it turns out that the graph of f is concave upward on that interval if the derivative is increasing, and concave downward if the derivative is decreasing on the interval. So concavity measures the curvature of the graph, or lets us know when there's curvature. So there's an official test for concavity. So if you take a look at that definition, if you think about doing work on the first derivative function, just like we did on the original function to find relative extrema, you would basically find the relative extrema for the derivative function in order to figure out your concavity, right? So what's going to happen is, and this confuses a lot of people, but what happens is you run what appears to be the same test as we did to test for relative extrema, or to test for intervals where domain intervals where the function was increasing or decreasing. But now we'll be running the same type of test, but we'll get different information about the original function, and we'll get some information about the derivative function. So let's just kind of take a look here. So this here would be our original function f, okay? So this is, x, and this is f at x. And so what I've done is I've drawn a bunch of these little tangent lines. What you'll see is here the original function is increasing. Would you agree? From here to here on the graph, right? And then so at some point you'd have a zero derivative. So all of these slopes, if you imagine the slopes of these tangent lines, what are they doing? Do you see it's very, very steep right here? Very positive, steep slope. And then it's a little less steep, a little less steep. And then it would go to horizontal, and then it would start to go to negative. And so right here from about, I don't know, approximately, I'll do this in green, probably about right here, you've got downward curvature. So the derivative function is decreasing, okay? And so this, because the slopes are decreasing, and the original function is curving downward. And then there's a change at some point. And then what will happen is you'll have an upward curvature here. So from approximately here to maybe, I don't know, here, we don't know what's going to happen. We'll just continue drawing it out. We don't know how, if we just assume this graph is going to behave, the same way, we'll do that. But do you see that we've got it curving upward? And what's happening with the derivative, with these tangent lines, their slopes? Do you see this is a very steep negative slope? This is not as negative. And then we go to 0. Then we go to positive. So f prime on this interval here is increasing. So if you kind of look here, f prime is greater than 0. No. So what we see right here is that the original function is curving upward, all right? And our derivative function, f prime, is increasing, right? And then from over here, do you see that our f prime is decreasing? And of course, we'd be dealing with, domain intervals. Like that. Good so far? All right. So there's an official test for concavity, and it's really pretty cool. So here, if you let me get this a little bit smaller. Okay. So this test for concavity basically says, hey, if the second derivative is positive in the interval for all x, then your function's going to be curving upward, concave upward on the interval. So basically, think about your first derivative, right? If your first derivative has an input value where there's relative extrema, right, then meaning that we set the second derivative equal to 0 and solve for those numbers, then basically, you can do that same test to see if the intervals on the derivative function are increasing or decreasing, right? So basically, if you have an increasing slope function, then you're going to have upward curvature. And if you have a decreasing slope interval, then you'll have downward curvature. All right? So keep that in mind. All right? So here we go. We're going to take a look at this function, and we're going to identify the open intervals on which the function is concave upward or downward, right? So first off, what do you think we should do? We'd be finding the zeros of the second derivative, right? So what will we get? So we have our y equals negative x cubed plus 3x squared minus 2, differentiating both sides with respect to x. We will have y prime at x is equal to negative 3x squared plus 6x. Good so far? Now we have to take the second derivative. So differentiate this guy with respect to x, and we'll get y double prime at x is equal to, beautiful, negative 6x plus 6. Finding the zeros of the second derivative, I'll go ahead and factor out that negative 6, and I'll get x minus 1, sorry. All right, so then we would get that, 0 is x minus 1, because that negative 6 would divide out. So x equal to 1. You also have to take into account if there's an input value that exists on the graph where the function's not differentiable, but that won't affect our function here. Okay, so here we go. Run the test, right? Gotta run the test. So now the trick here is our test is run on using the second derivative. Beautiful, right? So here we got 1 as the value that zeroed out the second derivative, the input value. So we only have 2 intervals to test. It would be going from minus infinity to 1 and 1 to infinity. And so just as a reminder, our second derivative, I used y. Our second derivative function was equal to negative 6 times x minus 1. So what should we test in these intervals? How about 0 and 2? Does that sound good to you? Awesome. All right. So here, y double prime at 0 will be negative 6 times 0 minus 1, which is positive 6, right? So which is greater than 0. So we get a positive here. And then y double prime at 2 is negative 6 times 2 minus 1, which is negative 6, which is less than 0. So all I did is I plugged in these test values into the second derivative function. So this information gives me information about concavity for the original function, and it also lets me know that the derivative is increasing from minus infinity to 1 and decreasing from 1 to infinity, right? So all kinds of great information. So now, here we go. What's our conclusion? Well, y is concave upward on minus infinity to 1 because it had a positive interval for the second derivative, and concave downward on 1 to infinity. All right? Very cool. So let's take a look at a picture of this, because I want to lead into when we talk about the second derivative test. Okay, so it'd be interesting to see what all these things look like. So what did we have? Negative x cubed plus 3x squared minus 2. Negative. Okay, so that will give us the blue will give us the graph of the original function. The green will give us the graph of the derivative function. And then, hey, let's do this. Why don't we also do the graph of the second derivative function? So to do that, we'll go into math, and deriv is 8. And then we're doing this derivative with respect to x. And we want to do this on the variable y2. So we go to y's, y-var's function, and then y2. And then we want it for all x. So we'll just say x is x. All right? So ready? Let's do, let's try Zoom standard, and then we'll see what we need from there. That's the original function. It's our derivative function. This one will take a little longer. It's got to think more. And that is our second derivative function. So let's take a snap of that. Okay, so we'll do it right here. All right, so let's check this guy out. We've got, this guy is, the blue is y, the green is y prime, and the black one is y double prime, right? And if you take a look here, I'll get the little hand tool. So here, like we learned the other day, at the zeros of the first derivative, that's where relative extrema occur, right? So the first derivative is 0 here. The original function has a relative minimum here. And then again, derivative function is 0 here. Original function has a relative maximum there. Now let's take a look at what happens with the first derivative and second derivative. So when the second derivative is 0, right, then see how the first derivative has a relative maximum there? And what's happening with the original function? Do you see how it changes from curving upward to downward? So here we had upward curvature from here to about here, and then downward curvature the rest of the way. So it's really amazing how much these derivative functions can tell us about the original function and each other, right? Very awesome. So now let's think about this. If when you're curving upward, so look at this yellow here. We're curving upward here, right? If you are on an interval where you're curving upward and there's a relative extremum there, doesn't it have to be a relative minimum? Does that make sense? You're curving upward, so at the zeros of the first derivative, you're going to be having potentially a relative minimum. When you're curving downward, right, on an interval, at the zeros of the first derivative is where you will have a relative maximum potentially. So that's really what the second derivative test is all about. It basically says, hey, if when you evaluate the second derivative at those critical numbers for the critical numbers for the function, right, by setting the first derivative equal to 0 or finding out where the original function is not differentiable, basically if you evaluate the second derivative in if you evaluate the second derivative at the critical number or numbers from setting the first derivative equal to 0, then what will happen is if you get a value that's greater than 0, it's occurring when you've got upward curvature, which means you'll have a relative minimum. All right, so keep that in mind. And if you get a less than, of course, that extremum would be occurring on an interval where you have downward curvature, and so that would mean you have a relative max. All right. Okay, so let's do this next guy, and if you want, go ahead and pause the movie and then see how you do. So here the directions are the same, so we need to find the zeros of the second derivative, and to do that we have f at x is equal to, we could write this as x plus 2 times cosecant at x, couldn't we? Right, using reciprocal identity. So now f prime at x, when I differentiate both sides with respect to x, will give us f prime at x equals 1 minus 2 times cosecant at x cotangent at x. And then now to find the zeros of this derivative, all right, differentiating again with respect to x so we can get to that second derivative, we will now have f double prime at x is equal to, the 1 will zero out, so we'll have negative 2 times d dx of cosecant at x times cotangent at x plus cosecant at x times d dx of cotangent at x. That's using the product rule. So f double prime at x will be negative 2 times. So let's see, the derivative of our cosecant function is going to be negative cosecant x times cotangent x. But we have another factor of cotangent x here, so that'll be squared. And then over here, we'll have plus cosecant at x, and then times d dx of cotangent at x is negative cosecant squared at x, right? So f double prime at x will be, you see all terms have a negative, so that one, negative times a negative times a negative keeps that negative. We'll just have one, oh, fuck, what am I saying? So the terms will all go positive since you've got a negative factor and two negative terms. So then what we'll have is we can factor out a cosecant at x, and then what we'll have left is cotangent squared at x plus cosecant squared at x. So now we need to find the zeros of that. So does the cosecant function ever have an output of 0? No, right? Because it's got its range that goes from minus infinity to -1 inclusive, and then 1 inclusive to infinity non-inclusive. So when we set 2 cosecant at x equal to 0, that's an extraneous answer. It's not possible. So that gets thrown out. That wasn't the factor that was 0. Now let's take a look at the, cotangent squared at x. I seem to remember that there's an identity, right? So we have 0 is cotangent squared at x plus cosecant squared at x. So 0 is going to be cotangent squared at x plus 1. Or I'm sorry, you would have cotangent squared at x plus 1 plus cotangent squared at x, and for cosecant squared at x. So that would give us 1 plus 2 times cotangent squared at x. So then we'd have 0 is actually 1/2, negative 1/2. Let's write it like this. So we would get cotangent squared at x is equal to negative 1/2. And then notice that you'd have to square root both sides, and that's not possible. So this is another extraneous answer. How mean is that? All right, so what was the other thing that you would look for? You would look for the domain values where the function is not differentiable, or where there's some sort of a domain restriction, right? So here, do you see when x equals 0, one over sine at x is undefined, right? So that's not part of our domain. So now we would have that value. So we need to use x equals 0 to divide up the number line. Okay, so when we run the test, that is what we'll use. So we'll have, this was minus pi to pi, and then we're going to be using 0, right? That was an input value that causes a discontinuity. And so we'll have minus infinity to 0, and then 0 to infinity. So we run the test in that second derivative function, right? So that guy is, it's actually right up here, right? This second derivative function. So let's check it out. F double prime at, you want to check, let's see. How about we check negative pi over 2 and pi over 2. I think that'll be all right. So F double prime at negative pi over 2 is going to give us what? So we'll have 2 times negative 1 times the cotangent function will zero out, and then we'll be squaring the cosecant function, so we'll get a positive 1. So that's equal to negative 2, which is less than 0. And then checking F double prime at positive pi over 2, that's going to give us 2 times 1 times 1, which is positive 2, which is greater than 0. So what's our conclusion? On minus infinity to 0, F is concave downward, and on 0 to infinity, F is concave upward. All right. Okay, so now we get to definition of point of inflection. All right, so a point of inflection, basically, go ahead, read through the definition, but to make a long story short, what happens is if there is a change of concavity at an input value, right, that exists on the graph, right, so when the second derivative is equal to 0, then you have a point of inflection. If there's no change of concavity, there's no point of inflection, right? So going back to the examples we just did, the first one would have a point of inflection, wouldn't it? Because 1 exists on the graph. So there'd be a point of inflection at 1, and then the function evaluated at 1. But here, since the way we divided up the interval was from a discontinuity, that means that we would not have a point of inflection even though there was a change in concavity. All right? Okay, so now let's take a look. There's a theorem, of course, for points of inflection. Assuming C, comma f of C is a point on your graph, right? It will be a point of inflection if it's a point of inflection, then either the second derivative evaluated at that input value is 0, like we talked about, or the second derivative does not exist when x is c, but the original function does, all right? So let's check it out. What do we do for this guy, for g? They want us to discuss the concavity. So again, let's find the zeros of the second derivative. There's no input value where this function is not differentiable, so we'll be fine. So g at x equals 2x to the 4th minus 8x's plus 3. Differentiating with respect to x, we'll have g prime at x is 8x cubed minus 8. Now we need to differentiate again with respect to x, and we'll get g double prime at x is equal to 24x squared. Good so far? Now, finding the zeros of the second derivative, we get that x would have to be 0. Good so far? Awesome. All right, so running the test, we have So here's our setup. Okay, so now take a look at that second derivative function. G double prime at x is equal to 24x squared. Is that ever going to be negative? No, right? You're multiplying by a positive number, and when you square any number, you're going to get a positive unless it's 0, right? So do you guys see that any test value, let's say we picked -1 and 1, G double prime at -1 is going to be greater than 0. G double prime at +1 is greater than 0. So basically, both of these intervals are positive. Now, so what happens is, what's our conclusion? Well, G is concave upward on, now be careful, G double prime at x is 0 when x is 0, so you're neither concave upward nor downward right there. So we'd go from -infinity to 0 union 0 infinity. Okay? Now, are there going to be any points of inflection? The value x is 0 exists on the graphs, right? So that checks out. But is there a change in concavity? No, right? So there's none. I'll put in parentheses, since there's no change in concavity. Okay? How you doing? Awesome. All right, so we've talked a lot about the second derivative test, all right? So basically, this is where we examine the curvature of the function at the critical numbers for the function, all right? So the only bad news about this test is if you get a result of 0 when you evaluate the zeros of the first derivative in the second derivative function, the test fails and you need to go back and run that first derivative test, all right? But if you get greater than 0, right, that means that at the relative extremum for f, the function is curving upward, which means you'll have a relative minimum. And so for f double prime at c being less than 0, that means that you're curving downward. The function's curving downward at its point where relative extremum is, so it's a relative max. All right? So let's check it out. All right? We find all relative extrema, use the second derivative test where applicable. Now, I don't know about you guys, but here, this function here, it's easy, right, to differentiate and find the second derivative of. If you have something real complicated, you might want to just find the first derivative and then use the first derivative test. Okay, so f prime at x is good. 3x squared minus 10x plus 7. Now, remember, we need to find the zeros of the first derivative because we're going to be evaluating the second derivative at those zeros. So this guy is going to factor as I think it'll be like this. There we go. So we get that 3x minus 7 is 0, or x minus 1 is 0. And this would give us that x is positive 7/3, or x is 1, right? Which means that our C1 is 7/3 and C2 is 1. Good so far? Awesome. So now I'm going to bring up what we got for f prime before we started messing with it. Okay, so now differentiating both sides with respect to x, we'll have f double prime at x is equal to 6x minus 10. And so now, so the first one was find the critical numbers, right? Second step was find f double prime. Now third step is evaluate f double prime at the critical numbers. So f double prime at 7/3 is going to be equal to what? 6 times 7/3 minus 10. So I'm plugging in 7/3 wherever there was an x in the second derivative. And this is going to give us what? Which equals 4, which is greater than 0. So let's think about this. At 7/3, which is a critical number for our function f, our graph is curving upward, right? Curving upward because we have a positive value for the second derivative. So that means that there must be a relative minimum there, right? That's what that theorem says. And then f double prime at 1 is going to be 6 times 1 minus 10, which is negative 4, which is less than 0. And so this implies that since we're curving downward at the critical number 1 for the original function, that means that there's got to be a relative max there. All right? So now, what's the next step? We should find the corresponding y values so we can give the ordered pairs. So now, our original function was what? X cubed minus 5x squared. And then plus 7x. So we need to find f at 7/3. So that's going to give us 7/3 cubed minus 5 times 7/3 squared plus 7 times 7/3. And that will be equal to, I'm going to use the calculator on this one if you guys don't mind. And then what was it? Minus 5. Whoops. Times 7/3 squared. And then our last one was plus 7 times 7/3. Okay, so that gave us a decimal amount. Let's go ahead. You can change it into a fraction doing this command. So we get 49/27. And then this one will be easier. F at 1 is going to be equal to 1 cubed minus 5 times 1 squared plus 7 times 1, which will be 1 minus 5 is negative 4 plus 7 is 3. And finally, our conclusion. So we said relative minimum at 7/3, right? So there's a relative minimum at 7/3, comma, 49/27, and a relative maximum at 1/3, right? So we you just use the second derivative test to find relative extrema, all right? Okay, so now we've got this function here. Let's see how much more we have for today. Just a couple more problems. So we've got this function here. Now, I don't know about you guys, but I think I'm going to just use the first derivative test because we'll just see what the derivative ends up being. If it's a mean first derivative, I'm just going to use that first derivative test. Okay, so differentiating both sides with respect to x, we have f prime at x equals, so remember we're going to be using that quotient rule, so d dx of x times x minus 1 minus x times d dx of x minus 1 all over x minus 1, the quantity squared. So f prime of x will be 1 times x minus 1 minus x times 1 all over x minus 1 squared. F prime of x, simplifying, will be x, let's see, minus 1 minus x is just going to be negative 1 over x minus 1, the quantity squared. And this guy, do you see, is not going to have any real zeros, right? So this is what I'm thinking, you know, we don't want to use a second derivative test on this because there's no critical numbers. The number that we're going to use to divide the interval is going to be 1 because that yields a vertical asymptote. So no real zeros for f prime. So that means we got to use, when I'm going to go ahead and run the first derivative test instead, okay? So doing this one, we use the 1 because that's the input value where there's a domain issue. And so we'll just have 2 intervals to test. And we're testing them, remember, in f prime of x. So what do you want to test? How about 0 and 2? Does that sound good? Awesome. So then f prime at 0 is negative 1 over. Okay, so we'll have negative 1 over 0 minus 1 squared, which is negative 1, which is less than 0. And then here we'll have f prime at 2 will be negative 1 over 2 minus 1 squared, which yields negative 1, which is less than 0. So what do we conclude? There's no relative extrema. All right. So here we come to our last example. Thought I had a graph. Huh. Our last example here. So let's see. Get a grid going. This guy is asking us to, make a picture of a function f that has these characteristics. So here we go. So this is going to be, we're going to be making a graph of f of x, and we've been given this other information. Some of it's from the original function, some of it's from the derivative function, and some of it's from the second derivative function. So you got to be kind of a math detective, right, to figure out what to do. So let's just have a scale of, I don't know, fives all around, okay? So what does this say? F at 0 equal to f of 2 equal to 0. What does that guy give us? What does this guy give us? Good. This guy gives us the zeros of the function, right? So that's what the yellow gives us. So let's go ahead and graph them, all right? So we've got ordered pair at 0, 0, and an ordered pair at 1, 2, 0. Good so far? Okay, so next up, this next information gives us information about, first of all, let's check this out. I'm going to skip down here. F prime of 1 equals 0. That's giving me the zeros of the first derivative, good, but what other information do we get from that, right? And it gives us the relative extremum of the function. So that gives us quite a bit of info, right? So what that means is we don't have the y value, right? But we can put it, we can use whatever y value we want, but what do we need to find out? What do we need to find out about that? We need to go to another piece of information, don't we? Good. We need to go to this guy to see what's happening. Is it what's happening on either side of that critical number? That's going to tell us if we have a relative max or min. So this one's going to let us know so we get information about the sign of the first derivative, right? And the whether or not, whether we have a relative max or min on the original function. Okay, whoops. So that also gives some great info, right? All right, and then lastly, we're going to get information about the curvature. So this guy here gives us information about the curvature of the function. So as far as the derivative, it would tell you where there's relative extrema for the derivative, but I'm going to focus on the I'm going to just say what it is. So basically, in the orange, this lets us know that F is concave downward because it's a negative second derivative, right? And it's on minus infinity to infinity. All right, and then oh, that other one also gives us information about the behavior. The sign of the first derivative. All right, so now we've got f prime is greater than 0 to the left of 1 and less than 0 to the right of 1. So that means that you're going from a positive first derivative to a negative first derivative, which is a relative. Good, maximum. So I'm just going to plot the point anywhere as long as I have an input of 1, and as long as it'll be a relative max, I'm good. And then we can finish drawing I'll just draw mine like this. And that is concave downward over its whole domain. So we're all done. All right. Have a fabulous day, and I will be talking to you soon.